on calculations. Although we already have a sense that whenever we try to compute something that contains error, it brought forward the error. But we just want to see how this happens. So what I am doing here is that let's say there are two quantities. For example, there is one quantity y and its approximate quantity is defined as y cap, and let's say there is another quantity, let's call it g, and its approximate quantity is defined as g cap. So we can clearly see these two contains error. So let's say the error in the y term is reflected by epsilon y. How it is defined? Y cap minus y bar. It is not absolute error, just an error. Similarly, epsilon g is an error, amount of error. It could be positive, negative, 0. That is the difference between the exact g quantity minus g approximate quantity. So this is just an idea. So from here we can conclude that if I want to express my exact reading, if I want to write down my exact reading, so exact reading would be, in this case, is y equal to approximate quantity plus error in y, if I know this error in advance, and exact quantity of g is equal to approximate quantity plus error in g. So let's use these two as a reference on the onward slides as well. On the onward slides as well. So and whenever I need to use y, I can use y cap plus some error from in it. Whenever we want to use g, I can use g approximate plus error part. So in general, I can say exact value equal to approximate plus error part. That's true. If we know the error, we add it or subtract it in our approximate value, we will get the exact value. But that's the main point. We don't know the error because we don't know the exact quantity most of the time. But let's say this is. So what I want to do, I want to see the impact of this error in a simple calculations. And whenever we say calculations in arithmetic, we want to basically perform simple arithmetic operations. So let's focus what happened if I try to, my intention was to add the exact reading. So I will try to add y and g. But due to the problem in our calculations, we know that we want to perform the following calculations only. So let's see what happen if I try to add. So number one, impact on addition. So addition, let's check. It's very simple concept. It's just to have an idea that when we are doing calculations, we make very simple approximation. Okay, leave this decimal. Okay, let's do. But whenever we do these kind of small changes, we end up error in our calculation. So let's see how the error propagate or what impact the error brought. So let's say I am interested to compute y plus g. These y and g belongs to the last slide. So in other words, whenever I want to compute basically instead of y, I can write down y cap plus epsilon y plus g yg plus epsilon g. So if I look to this part, I can clearly see y cap plus yg can be kept together because these are the approximate values of same type, and epsilon y and epsilon g are together. So we can clearly see the same principle that I showed at the back stage. Last slide, in fact, I have to write down again here. Exact value is equal to approximate value plus error. This also exists there. So what does this mean? My intention was to add two exact values, but I do not have an exact reading of these two numbers. In fact, I have approximate readings, which means y contains some amount of error. If I add that error back to it, I will get the exact reading. So add these two numbers and these two numbers. So what I will end up, I can see that adding two numbers that contains the error y cap and g cap basically is just adding their errors. So sum of two numbers which contains error is equal to the error in the sum of the two quantities, which means that error will be add up. That's the interesting point. So if you are adding two numbers that contains error, let's say 0.1 and 0.2, so the total error would be in this case is 0.1 plus 0.2, that is 0.3. So error will be add up arithmetically. Obviously, if epsilon g is negative, it will cancel out as well. But I mean to say they try to add up, algebraically add up. So this is the interesting point. If you are similarly, if there are 4, 5, 6 numbers that contains error, individual error will be add up. So this is one of the observation. Similarly, one can clearly see you can do the same thing for difference as well. So I should not put head, but let's say if I want to do understand subtraction, what happen when I subtract two numbers that contains error? So let's say I want to compute y minus g. So basically I have to compute y hat minus epsilon y minus plus this quantity g cap plus epsilon g. So if I compute this quantity, I will get y cap minus g cap plus, okay, what I have to plus, that's interesting, epsilon y minus epsilon g. So temperament of the reading is still the same. Exact quantity, that the difference of the exact number is equal to difference of the approximate while adding error differences. That is the difference of the error will be added. So which means that if you have a two number that contains error, and if you want to add those two numbers, or in fact subtract these two numbers, so you get an answer that contains the error, which is the difference of the individual errors. So this is also important point, because sometimes this error will be cancelled out because of the same magnitude. For example, here you get 0.1 epsilon y and you get zero point 0.1 of epsilon g. So when you put this here, you will cancel out these two quantities by magnitude. So you can see that sometimes in subtraction, approximate quantities can behave like a exact reading or as well, but they are not. In so this is one of the interesting point as well. So what we have learned from here is that if we add two numbers that contains error, that the total reading will contain the error which is equal to the sum of the individual errors. Similarly, if we subtract something, we will get an error in the final answer which is equal to the difference of the individual errors algebraically. So that's the main point. Similarly, it is now easy. I will do one more calculation on multiplication as well, and you can do same for difference division as well. So let's see what happened when we have a number 3 is division. Sorry, multiplication. Multiplication. So let's do the same thing. So here I want to multiply y by g, which means that I have to multiply y cap plus epsilon y into g cap into epsilon of g. So if you multiply these two quantities, you will get the following calculation. So let's do a simple multiplication. Y cap into yg. I hope you understand what I am doing. It is plus sign, not multiply. This is plus sign. Okay, so this quantity multiplied by this quantity plus y cap epsilon g plus g cap epsilon y plus epsilon y epsilon g. So this is the interesting point. So far, that is when we are doing addition and subtraction, we have seen that the individual error will end up or subtracted in the final reading. But here we are, when we want to multiply something, we are noticing that the error propagates very fast, because if there is no error, then epsilon g, epsilon y are 0. So this whole term goes to 0, which means that this term is error. So from here to here, these all terms contains error. So we can say that in case of multiplication, the final amount is not just a multiplication of the error term. In fact, that term also exists, but there is some other terms as well that generates the error, in which we multiplying the approximate value by the error of the other quantity. This means that the error in case of multiplication propagate faster. Multiplication propagate very fast. It quantify faster because this is not just a product of the two multiplication terms of the individual error. It is also because error are usually very small, so when you multiply a small quantity, this part can be negligible. But the problem in here, these quantities are large because they are just like comparable to the original value. So when you multiply these two quantities, the total error part, that is epsilon terms, is very high. So what we can say that the total error in case of multiplication impact higher than the addition and subtraction. That's the important point. So be aware that when you are making truncation error, round off error, or any sort of machine error, and you want to use them during the calculation, so keep in mind that you are brought forward the error. For example, let me give you a simple idea. For example, you just using any instrument, you computed the current and a voltage, but these are approximate reading because you came to know that the instrument that you are using is wrong, is giving you some mistake reading. So when you want to compute the using these readings, when you want to compute the power, for example, and we know that the formula of power P is equal to VI. So basically what you want to do, your intention was to multiply correct voltage by the correct current to get the power. But your instrument contains the error and it will give you two readings, I cap and V cap. So you don't know the exact reading, so you multiply V cap and I cap. And as soon as you multiply these two terms, you will get a certain number. So you think that this is the exact power, but no, because V cap and I cap both contains error due to the machine or any other source. So when you multiply the wrong approximations together, their approximation, they are close to V, close to I, but they contains error. So when you multiply these two, so this whole term will be there as well. So in the exact reading, it is not just a product of this thing. You have to think about a big term of error as well. So multiply is very dangerous thing when you have an error because it propagates the error faster. It's just an example. And similarly, I'm not adding this time. You can do the same calculation for division as well. You have to apply some binomial formula and simplification. But the point is error propagates in division as well. Multiplication faster as compared to addition and subtraction. And what are the quantities? For multiplication, the error amount is by this equation, and in addition, the total error amount is this, and in subtraction, total amount error is this. So student, I hope we have a time, so let's finish this part as well. So I want to compute somehow y upon g, that is division of two quantities. Whenever I want to do, basically in this case I want to compute this quantity. I hope you all can understand what is the problem we have, because it is dividing this quantity. So what we have to do, we have to compute something called y plus epsilon y into g cap plus epsilon g inverse. This denominator will be brought on the top of side of this calculation. So we can clearly see when I expand this formula epsilon y. So here I have to expand this term. So here the term that we want to expand is from the series expansion. So what we will get here, if or we can take out some other term as well. So let's do it like that. If I take out, let's say g bar here, is common from it, so I will get g sorry g cap upon epsilon g. uh, Sorry, if I take only g bar common, so I will get 1 plus epsilon g over g bar, -1, and this will also take the power negative 1. So it's just a common, I take the g bar from this last part, g bar. So if I take g bar, so in other words, this could be, because this g bar is 1 over, so I can write it down like that, y cap plus epsilon y upon g bar into 1 plus epsilon g upon g cap inverse. So here I have to apply a binomial series formula to open this term, and then what we have to do, have to multiply this whole factor. But I'm not going to further in this detail, because the point that I want to establish is there. If there is no error, then the final answer would be y over g equal to y cap over yg, because approximate and exact value are same because there is no error. But we can clearly see in this case, when I apply the Taylor binomial series expansion, I will get 1 plus nx and n minus 1 and so on. Obviously I have to truncate the terms. So whenever I multiply this term with rest of the terms, y bar over yg is always exists along with some epsilon y and epsilon g terms, which means that in case of division, propagation of error becomes more complicated. So this is the only point that I want to establish here. So final answer would be something like y cap upon g bar plus some terms of epsilon y, epsilon g, these type of terms. But we are not interested to compute. The point that I want to establish, that whenever you have to compute the division as well, the error term becomes more complicated as well. So the point is, now what you have to think. For example, you want to perform a simple calculation, like you want to compute uh, this term y plus g divided by y multiplied by g. Now student, you can clearly see that y and g and y and g. So you know that if y and g, these quantities contains error, then the numerator contains the error sum of these two quantities. Because we know that if I add two quantities that contains the error, then the exact approximate quantity plus the error part is yg epsilon g. And if I multiply these two terms, then I will get some denominator contains more error terms, and then I have to divide those terms as well. So then at the end it becomes so much calculation involved representation. But the point is, if in individual calculations like this one error exists, then when we try to perform further calculation by doing multiplication, addition, division at the same time, then error propagates much worse, or it get or more what you call it, more predominant in the calculation. So student, whenever you are using your instruments, at the end you are performing any calculation, you should be clearly aware of that, while what causing the error, and whether having this error in a calculation is a good or not, and if it is contains the error, then can you quantify this error as well, because this is the most important part in the engineering applications as well, and other mathematical problems as well. So student, this is the so far the lecture that we have discussed, and mostly is related to the error part analysis and error computation as well. So this is the point that we have now. So here I would like to end the first lecture. as well, and thank you for your time, and I also request you to